All right, so here we are, first of our series of lectures on muscles. And again, like we did with the skeletal system, I am not expecting you guys to know all of these muscles. And honestly, the muscles in this picture, these are the main ones. These are the biggest of the muscles in the body. By the time you start getting into some of the finer muscles, you're looking at maybe 400 or so different muscles in the human body. So much more than we want to go into for the purposes of this class, but more importantly, I think we're going to get a sense for um, how muscles function, especially skeletal muscles. So that's kind of the overall plan here. Is we're going to start off just like we did the last chapter, looking at the overall functional characteristics of muscles. We'll look at muscle contraction. We will look at where we get the energy from muscle contraction. Take a look at slow twitch versus fast twitch, and then end up talking about how muscles are made. So with muscles, we're now on the left side of the picture, right? So we're looking at contractile cells. And again, our focus is going to be more on skeletal muscles. We've already seen the framework of the body. Now we're going to see the motors of the body. So we've already seen how the skeleton relates, right? It's great to have muscles, but you also have to have attachment to something to allow something to move as a result of that muscle contraction. So the skeleton and the muscles are very integrated with one another. They're often described as the musculoskeletal system because you really can't have one without having the other one. It does you no good to have a skeleton unless you have something to move the skeleton. It does you no good to have muscles unless you have something that you're planning on moving. All right, so different characteristics of muscles. They are excitable, so we're going to take a look at what happens when a neuron, for example, releases a neurotransmitter and how the muscle cell responds to the neurotransmitter by contracting. So there's going to be what we call a sliding filament mechanism of muscle contraction where protein fibers walk past one another and shorten the overall muscle itself, and that then is going to produce some movement. Muscles are also extensible. So in addition to having contraction, we can also have extension. We can have flexing. We can have extension. There is the equal and opposite movement sort of idea going on here with these. And muscles are also elastic. So there's a tendency for muscles to kind of bounce back to the original configuration once contraction is over. Right? So we've already looked at different types of muscles. We saw this back in our chapter on animal organization and homeostasis. We saw skeletal and cardiac and smooth muscle. We looked at characteristics of each. We talked about how the skeletal muscles and cardiac muscles are both striated. We talked about how cardiac muscles and smooth muscles are involuntary, whereas skeletal muscles are voluntary. So we've kind of already seen the basic fundamental differences, I guess histological differences between the different types of muscles. Again, the primary focus of this chapter is going to be to look at skeletal muscle, although at least with the cardiac muscle, contraction works in kind of a similar fashion. We've seen tendons as well. So again, most muscles are going to attach to a bone via a tendon as opposed to any other mechanism. Some muscles do attach to the periosteal layer of a bone, but in most cases, muscle attachment is directly to a tendon, which then connects to the bone itself. So now we have kind of the first glimpse here of what a skeletal muscle looks like with its organization. We have a tendon back here attaching to a bone. We then have the overall muscle itself. But if you take a cross section through that muscle and look at it, within this connective tissue, there are bundles or fascicles of muscle fibers. Now, the muscle fiber is a really important level of organization because a muscle fiber is also known as a muscle cell. They are the same thing. But if you zoom in even more, if you take a closer look at a single muscle fiber, what you're going to find is there are what are called myofibrils, which are the subcomponents of the muscle cell. And those myofibrils then, in turn, contain both thick and thin filaments, which are the contractile units of the muscle itself. They are the ones that actually do the heavy lifting, so to speak, when it comes to muscle contraction. Cardiac muscle we talked about, this is the muscle we find primarily only in the heart. They, like I mentioned a second ago, have kind of the same mechanism of contraction as do skeletal muscles. That sliding filament mechanism is almost identical in cardiac muscle versus skeletal muscle. Only in the cardiac muscle, contractions are what we describe as being self-initiated. So the heart itself, when we talk about the circulatory system, when we talk about the circulatory system, we will take a look at the cardiac cycle. We'll consider what happens to initiate the cardiac cycle, what begins the heart beating itself. It's initiated by something called the SA node, or the sinoatrial node, which is kind of like the pacemaker of the heart, which causes the other cardiac muscle cells to contract in turn. We've also seen gap junctions before, so you kind of get a sense now for why we've laid some of the groundwork that we have. Why do we talk about cells and cell connections? We've got gap junctions. Gap junctions are cell-to-cell connections in cardiac muscle that allows for these signals to pass instantaneously from one cell to the next, to the next, to the next, to the next. So the entire thing, the entire heart itself, actually contracts as a single functional unit. And there are action potentials. We didn't go into, in our discussion of the nervous system, the idea of what action potential is versus resting potential. But an action potential is what initiates the beginning of a contraction. So when a nerve cell fires, we'll just call it firing for now. When a nerve cell fires, when a neuron fires, that's going to cause release of neurotransmitter. That neurotransmitter can then cause the beginnings of cardiac muscle cell contraction throughout the rest of the cells, kind of in line. Smooth muscle, on the other hand, is visceral muscle. That's what we find lining arteries and arterioles, blood vessels, primarily those two, arteries and arterioles. We find it in digestive organs. We find it in the bladder. We find it in the uterus. We find it in along the gastrointestinal tract, all the way through it, from the esophagus to the stomach to the intestines, both large and small. There is smooth muscle there as well. There are no striations, so we know smooth muscle is non-striated muscle. It doesn't have the orderly arrangement of fibers like we see with cardiac and skeletal muscle. We also know smooth muscle is involuntary, so you don't control it consciously. Contractions tend to be slow and sustained. There's not this explosive power that we see with either cardiac or skeletal muscle, so it's a different kind of a muscle altogether. But very important, certainly, when it comes to vasodilation, vasoconstriction, or moving the remnants of your meal down your gastrointestinal tract. So in this case, smooth muscle is controlled primarily by stretch receptors, by hormones that might be released, like oxytocin that we've seen before. The nervous system directly might control it through the use of different kinds of input as well. The hormones involved with gastric motility, for example, are a way the nervous system communicates with the digestive tract. The skeletal muscles now are voluntary. These are the ones that you probably know best. They're the ones we control by thinking about them. And skeletal muscle is just that. They are muscles that actually move the skeleton. So the functions of this obviously are movement, right? If we're going to walk down the road, if we're going to pick up an object, we have to have some sort of muscle allowing our skeleton to move. Maintaining posture, supporting internal organs. A lot of skeletal muscle is involved with keeping some of the internal organs in place. We have, when it comes to veins especially, but also lymphatic vessels, we mentioned with arteries and arterioles, they have smooth muscle, so they can cause them to vasoconstrict or vasodilate. Veins and venules, or smaller veins, don't have that degree of smooth muscle. So what they're going to have instead is they're going to be surrounded by skeletal muscle that when you contract skeletal muscle, when you move around, when you walk, when you do any kind of activity, that's going to kind of help push blood through the veins back toward the heart. So skeletal muscle actually, believe it or not, does serve a cardiac or a circulatory function, just like smooth muscle performs a circulatory function with arteries and arterioles. Shivering is also initiated by skeletal muscle. So when you're cold, when you shiver, these are contractions of skeletal muscle that generate heat and help to raise body temperature. And so again, we see this idea of antagonistic muscles. If we look in this picture here, we have a pair of antagonistic muscles. We have the biceps over here. We have the triceps back in the back part of the upper arm. If we want to flex the arm, we have to flex the biceps and we have to relax the triceps. If we want to extend the arm down, then we have to relax the biceps and flex the triceps. So they're antagonistic. They move in opposite directions. And if you want to move, you must contract one and relax the other one. Synergistic muscles, on the other hand, are muscles that work in coordination together. So if you were to look at the muscles collectively you would call your quadriceps, or the muscles you would call collectively your hamstrings, those would be good examples of synergistic muscles that work together to produce some sort of motion. Okay, so that's our other type of muscles working together and how they work. So we've seen muscles attached to bones. I talked briefly a few minutes ago about how muscles can sometimes attach to the periosteum, which is the outer layer of tissue surrounding bones. We talked about that back in our chapter on skeletal system. Or we can have attachment through tendons. So sometimes muscles attach via tendons to the periosteal layer. The connection is not direct, but it is a connection nonetheless. Now, when we look at muscle function, the part of the muscle that doesn't move is called the muscle origin. The part that stays stationary during contraction is called the origin. The part that actually moves along with the bone that it's attached to is called the insertion. So we talk about insertion, we talk about muscle origin as well. One of them moves, one of them doesn't move, one of them stays stationary. Okay, so we take a look here at the movement of the lower part of the leg. If we want to flex the leg down, like if you're doing leg curls, then you're going to flex the hamstrings and we're going to relax the quadriceps group. You cannot flex your lower leg if your quadriceps are tensed up. On the other hand, if we want to do leg extensions at the gym, then we're going to be contracting our quadriceps muscles and relaxing our hamstring muscles. So it's the opposite effect, right? We're relaxing one group and we're contracting the other group, and that's going to help us produce the desired movement. All right, now is when we're going to get into the actual function of skeletal muscle and how contraction actually works. But before we start telling the story of muscle contraction, we have to look at all the players involved. So the muscle fibers, again, are kind of going to be our main players in the story of muscle contraction. Muscle fibers or muscle cells are very long. They run in parallel. There are many, many of these together in a single bundle, which makes up the muscle itself. The myofibrils, then, are the subunits of the muscles that actually work more directly when it comes to the contractions themselves. So within the myofibrils, we find what are called thick filaments and thin filaments. And each one of those is made out of a different kind of protein, and each one of those is going to have its own role to play when it comes time for muscles to contract. A couple of other structures that we want to look at here on these pictures are the sarcoplasmic reticulum, which kind of goes in and around these myofibrils. It kind of permeates throughout the muscle cell or muscle fiber and allows for dispersal, or actually in this case, storage of calcium ions. The sarcoplasmic reticulum is responsible for storing up calcium ions, which are released at the beginning phase of the muscle contraction. The T-tubules in this picture are involved with allowing those calcium ions to permeate down and around the myofibrils to make sure that they get equal dispersion throughout the entire muscle cell itself, because those calcium ions are needed if those myofibrils are going to begin to produce a contraction. So again, here's our overall structure. We have the muscle itself, we have a tendon back here, and all the way in the background we have a bone, and that's what's actually going to be moved once this muscle contracts. The muscle again is made up of fascicles. Each fascicle consists of many, many muscle fibers. Each muscle fiber is made up of myofibrils. Myofibrils then are in turn made up of myofilaments, which can be both thick and thin filaments. There's a lot of hierarchy to this. It's kind of like a set of those what do you call them, Russian nesting dolls, where you've got a small doll that sits inside of a bigger one, that sits inside of a bigger one, which sits inside of a bigger one, and so on. It's kind of the same idea. It's a hierarchy of organization going from small to big, and each part has its own role to play when it comes time for muscle contraction. Now the thick filaments, right, these are part of the myofilaments that are making up the myofibril, which then in turn make up the muscle cell. The thick filaments are made out of something called myosin protein. And myosin protein has a shape kind of like a hockey stick. It's got sort of a straight line to it, and then it's got a little bit of a crook or a bend at the end of it. And those myosin heads that stick out are what's going to be most intimately involved when it comes time for muscle contraction. Now the thin filaments are made out of different protein. They're made out of what's called an actin protein. You remember back to our discussion all the way back in chapter 3, we talked about microfilaments in the cytoskeleton. They were made out of actin proteins. This is the same stuff. Actin protein is the main part of the thin filament, but it comes along with two what we call accessory proteins called troponin and tropomyosin. And troponin and tropomyosin are going to be involved when it comes time, again, for muscles to contract. There's going to be a linkage between the actin and the myosin, but for that to occur, troponin and tropomyosin also have to play their own role. So what we see in one of these myofibrils is an alternating arrangement of both thick and thin filaments. If you go down through there, what you're going to see are thin and thick and thin and thick and thin and thick and thin and thick. And what that does is it creates, because these alternating patterns of thin and thick filaments, that creates, in part at least, the striations that you see when you look at skeletal muscle. Okay. The sarcomeres, now if we look at the actual parts that do the contracting, if we look at one section of thick and thin filament together, we see what's called a sarcomere. Right? And these sections are really what shows up when you see the striations in skeletal muscle. What we see are thin filaments overlapping and alternating between thick filaments. And at the ends of these sarcomeres, we see what are called Z-lines. The actin filaments are attached to what are called Z-lines, which are what occur at both ends of any given sarcomere. Okay, so if we kind of jump back here a second, we see a sarcomere, single functional unit. If you zoom in on this, what you see are alternating patterns of thin and thick and thin and thick and thin and thick filaments. And then Z-lines are at the border of each sarcomere. There's a sarcomere here, and then also one on each side of it as well. which we see in less detail. So we talked about the SR a little bit. Sarcoplasmic reticulum, again, is involved with storing calcium ions. This is going to surround the myofibrils, and when it's time for the muscle to contract, there will be a release of calcium ions from the SR. And the T-tubules are how those calcium ions get from the SR into and around those myofibrils. So all of those protein fibers get equal dispersion of calcium ions once it's time for the muscle to contract. We'll take a look really quickly here at what happens with muscle injury, and then we'll get into here before too long. We'll take a look at muscle contraction itself and how that works. Tendinitis is where you have an inflammation of a tendon, usually due to an overuse of an elbow or a wrist or a knee or something like that. Fairly common situation. The tendon becomes inflamed for a little while. It's extremely painful. Once you have it, there's really no real good cure for it except for maybe some anti-inflammatories, but especially rest. Right? So if you have somebody who's playing tennis or racquetball or somebody who's running, you get tendinitis either due to an overuse of the muscle and tendon or a misuse, so you've got bad form perhaps, that's going to cause strain which could lead to tendinitis, or just simply getting older. Tendinitis seems to be much more common as individuals age as well. It takes a while to heal. That inflammation, for that to go away, can take days to weeks to go back to the previous state. It's not an overnight kind of a thing, and it's not something you can just push through either. It's painful enough that it will preclude you from using that muscle until you allow it to heal the way it's supposed to. So rest really is what you have to do for tendinitis. Muscle strain is either where you overstretch a muscle or you damage a muscle, right? So this could occur by lifting something that's too heavy. It could also occur by overstretching something, where you actually start tearing protein fibers in there. Again, the situation for this, you want to have rest. Ice is usually pretty effective for both of these as well because ice is a pretty good external anti-inflammatory agent as well. So ice is never a bad way to go for these things. So we're going to cut off here. When I start up with the next section, we were going to be on to contraction of muscles, which is kind of a story all unto itself. That's going to be the biggest section of this chapter that we're looking at next is on muscle contraction. So I will stop here and get ready to start the next section.